Okay, so I'm going to go over the mean value theorem, and I'm also going to go over the definition of the average value of a function. Now, what the mean value theorem officially says is that if you have a function f that's continuous on a closed interval a to b, then there's going to be some value c between b and a such that f of c times b minus a will be equal to the definite integral of f of x dx from a to b. Now, this may seem kind of abstract or, like confusing, confusing to understand, but it's actually pretty simple. And it's very important that you really take your time to go over this and make sure you understand it, because there's always a question in the free response section on the AP exam that's going to assess your knowledge of this. So really make sure you spend your time looking over the notes and doing practice problems, applying it. Okay, so to kind of give you a sense of what's going on here is that this is a rectangle. This is a rectangle. This is the height of the rectangle. This is the width of the rectangle. Remember, this represents the area underneath the function from a to b. So it's some area. Now, it makes sense for an area to, no matter what the shape of the area is, you can always, I guess maybe tangibly like rearrange an area into like some sort of rectangle that will have, equal that will have the same area. So like think of like maybe you have before I get to these diagrams, let's say you just have like an area underneath this, this curve here, underneath this upside down thing. The first thing you want to make sure you recognize is that this area can be basically configured to create some equivalent rectangle with the same area, so that we can maybe make a rectangle that's like maybe this size that has the same area of it. So this has, this area of this is equal to the area of this. So both these have equal areas. That's kind of what the main basis for this theorem is. Now, let's first look at how we can really understand, what it means by C and all that. Now, let's have F represent, this graph here. I have 3 pictures of it. And we're going from A to B. So we're looking at the area underneath, the curve, so the shaded area. Now, we can all agree that there's always going to be some area that's smaller than the total area underneath the function. So this rectangle represents some smaller area. This rectangle is what's called an inscribed rectangle, because it's all within the total region of the integral. This is inscribed rectangle. It's less than the total area. So the inscribed rectangle is this portion right here. Now, the width of this inscribed rectangle, remember the area of this inscribed rectangle is, the base times the height. The height of this is f of m. The base, or the width, is just b minus a. And remember, m is just some number, some value between a and b, and maybe it's probably like somewhere over here, I would say. It looks like the graph kind of, so m is probably going to be over here, right next to a. So that's in value between a and b. So that's what that's saying. So we're saying, essentially, you can rewrite this as the area of a rectangle, or you can write, maybe if you want, you can write this as an integral itself. But the area of this rectangle is just the height of this rectangle times the width, which is f of m times b minus a. Okay, now this is now before we get to this, this is what we call a circumscribed rectangle. This rectangle has an area that's larger than the actual area, as you can tell. This blue area. Circumscribed rectangle has an area that's greater than this. So let's use some inequality symbols. Let's write that this area is greater than this one, and this area is less than the true area here. This is the smallest area. This is the biggest one. And likewise, we can find some value large M, so that the height of this rectangle times the width, it will give you the area of that total rectangle. So the area of that large rectangle will be equal to f of large M times b minus a. Same principle. Height times the width. And again, probably the M value is probably somewhere up here. So large M is probably far to the right over here. So large M is between A and B, and small m is between A and B. Now the true area, again, let me just shade it. The true area, let's go, of the integral from A to B is, this area here, kind of, that helps. And what this is saying is that we can find a rectangle that has a width of b minus a and a height somewhere between the lowest height that's possible and the highest and the largest height, somewhere between f of m and f of large M. So in this case, the height of this rectangle is given by taking f of c, where c will be about here. So here, so this would give you a height of about, or exactly, this would be c f of c. The height of this rectangle is f of c, while the width is still b minus a. So that the area of this rectangle is equal to f of c times b minus a. So again, let me actually go write this out. This would be f of c, this length here, this height here. So the area of this rectangle here is equal to the actual area of the integral from a to b of f of x. So we call this the mean value. This is the mean value rectangle. So again, it's basically saying that you can create a rectangle where it will have a width that's the same as the length of from A to B, and can have a height that can be found by taking the function evaluated at C between A and B. So you can find some rectangle that's going to be between the size of this one and the size of the largest one that will have the same area as the integral. So again, this is simply the height of that rectangle, and this is just the width. That's all that's saying. Let me actually draw one little sketch over here just to kind of build some into, and this can work. You can test this out and see how it makes sense just by doing a sketch of any function. Let's do like some function like y equals x squared. And let's say we're going from 0 to, like, let's just say to 4 or something. So the true integral area is this. But what this is saying is that if we were trying to make a rectangle that has the same area, maybe it would be something like this, I would guess. I would guess it's something like, it would probably be something like that. Right? Something like that. And what do you know? Like this has the same width as the integral from 0 to 4, so it has a width of 4, and its height is found by evaluating c that's going to be between 0 and 4, right? That this will have a height again of f of c, and you could just again you can demonstrate this with just any drawing that you will make. So that's all it's the same. Don't overthink this, because I know some students that I've worked with kind of overwhelm themselves because they try to overthink it. It's just a rectangle, the height of the rectangle and the width of the rectangle. Now I'm using this, we can extend this, and we have the definition of the average value of the function, which is essentially just that f of c, because what you can do is solve this, or basically isolate f of c by dividing both sides by b minus a. So if you divide both sides by b minus a, let's move it over here. So let's have, we have this f of x dx equals f of x times b minus a. And let's say I want to get, not f of x, f of c. If I want to get f of c by itself, I would divide both sides by b minus a. Approach it just like you would in algebra. And what this is basically going to be rearranged or equal to, this is going to be the same as 1 over b minus a times the integral of f of x dx. And that would just be equal to what you have left over on this side, f of c. So it's essentially the same thing, and we call this the average value. This is known as the average value. That's it. The average value is essentially just the average height or the average y. That's what we found here. So that's all that's saying. They're basically the same thing, just rearranged. So let's look at the problem theory. How do we find it? How do we find the average value for this function on the interval from 1 to 4? So let's set this integral up. So average value, let's rewrite average value, will be equal to 1 over b minus a, 1 over 4 minus 1, times the integral from 1 to 4 of 3x squared minus 2x dx. So you're just solving this. You're just going to evaluate this. So this will be equal to 1/3 times, doing the antiderivative, 3x cubed over 3. Those will cancel, minus 2x squared over 2. Those will cancel, and we're going to evaluate from 1 to 4. So it'll be equal to 1/3 times x cubed minus x squared. So 4 cubed minus 4 squared minus 1 cubed minus 1 squared. So this will be equal to 1/3 times 4 times 4 times 4, 1664 minus 16 minus 0. So 64 minus 16, 48 times 1/3. So 48 over 3. And so then we'll have an answer of 16. So this is again just saying that the average height of this function on this interval will be 16. So we know that there's going to be some c value such that you can plug in the c value that's between 1 and 4 into this function and get 16. So that's all there is to it. So good luck.